record. All right, now it's official, we're being recorded. Again, my name is Kevin Weller, standing in for Bob Conway, who is out for this month. And I will present, let me go ahead and start this. Again, this is the Data Modeling Architecture and Integration Meetup. Let me figure out how to do this now. Let's see. Okay, share screen. Share it anytime. All right, so I'm going to share my screen. Make sure I got the right one here. This is the one I want. All right, can everybody see this opening slide?
Yes, great.
Yep.
I'm going to go ahead and make it an official presentation. Let's see. All right, so now I should dominate the screen. All right. Okay, so this is an introduction to spatial data integration by yours truly, Kevin Weller. I own Modern Geosystems. It's a consultancy. And so my professional background is in software engineering, though that typically involves working with many kinds of data. I've written code in many programming languages, including C, C++, COBOL, RPG2, various 4GLs, Perl, Ruby, Objective-C, and Python for everything from mainframes to mobile devices, for many industries, including natural resource extraction, transportation, hospitality, electronic components, software components, healthcare, online services, real estate, and communications. I started building web and other internet applications back in 1995, pretty much when they first became popular. Among other jobs, I worked for BEA, the creator of WebLogic, as a research and development engineer, then a software and program architect, till I left them in 2002. Then I was the CTO of a digital radiography firm for a while. So, x-rays, CAT scans, that sort of thing, until I founded my current company in 2006 to build web applications using Ruby on Rails. From the beginning, I was tasked to build one geospatial application, slicing and dicing land grid parcels from legal document land descriptions. I also happened to write half a book on Objective-C for Pearson, after which it was canceled thanks to Apple's decision to throw all their weight behind Swift. Most of my work since 2012 has been focused on geospatial data management, systems integration, application development, and business process automation using FME and Python. According to a 2017 article entitled "How Geospatial Analytics Can Give Your Business a Competitive Edge" in CIO magazine, roughly 80% of enterprises have some type of location data, even if it's just addresses or zip codes and addresses. With geospatial analysis, they can locate their customers on a map, see who is closest to them and to their competitors, and where they should put their next location. That 80% is a somewhat debatable figure. I've seen numbers as low as 71%, but it still represents a significant majority of organizations. When integrating data and automating business processes, spatial data is often overlooked and underutilized, despite being critical for success in the modern world. According to the Google Dictionary, spatial means relating to or occupying space. Examples of spatial data include geographic, like maps, addresses, specific locations on the Earth or other bodies, infrastructure networks like roads and gas lines, routes and navigation, jurisdictional boundaries, drone and satellite imagery, computer-aided design, or CAD drawings, three-dimensional models like building information management, or BIM, LiDAR results, and augmented and virtual reality, real-time sensor data, such as Internet of Things devices and GPS, or even medical and ground-penetrating radiographic images. Ignore this information treasure house, and your risks include building a new store or facility in a poor location, digging into buried electrical power lines, or violating property boundaries or industry regulations. In this presentation, I'll introduce some key concepts and broad applications. I'll briefly discuss common challenges inherent in working with spatial data, like incomplete or dirty data, incompatible coordinate systems and data formats, and lack of intelligible or timely access. Then I'll cover various options for overcoming these challenges using tools such as open source libraries, spatially enabled databases, and spatially competent integration tools such as Alteryx and FME. I'll provide some insight into which tools are best for which purposes. Finally, I'll end with a few examples of solutions from my own professional history. Let me start by introducing a few terms unique to the spatial realm. According to Kang-Soon Chang, I hope I pronounced that right, a geographic information system is a kind of database containing geographic data combined with software tools for managing, analyzing, and visualizing those data. A feature is equivalent to a record or row, and it can belong to a feature class or feature type, which is akin to a table or relation. A feature typically carries some kind of geometry, of which there are many varieties and subvarieties. I'll start by describing just a couple of broad categories. A vector is a way of representing geometry by employing one or more discrete geometric shapes defined on a Cartesian plane or three-dimensional volume. Examples include points, lines, curves, polygons, polyhedrons, and combinations of these to form more complex wholes. Consider the locations of retail outlets, the boundaries of a city, the shape of terrain for a given parcel of land, or the three-dimensional structure of a machine or building component. A raster is essentially a two-dimensional array of numerical values with fixed rectangular dimensions. The term comes from old cathode ray tube technology. Today, it's mostly used to describe graphical image files, such as those created by drone or satellite photography. But under the covers, it's just numbers. Those numbers can mean all kinds of things, such as elevation, slope, or temperature, as well as simple digital photographic pixels. Any of these can be represented as pixel grayscale or color values as well, even non-photographic values. An attribute is equivalent to a field or column in more traditional IS/IT language. These are of standard non-geometric data types, including character and variable with character, integer, floating point, decimal, date and/or time, Boolean, XML, JSON, and binary. Any feature can hold any number of attributes. Now, to put the geography into geometry, you need to understand that the Earth's surface is not precisely a sphere. It's technically known as an oblate spheroid, with the planetary diameter between the poles shorter by roughly 21 kilometers than when measured through the equator. Of course, the Earth's surface is rougher still, with oceans, tides, plateaus, and mountains varying from the average spheroid in locally significant ways. A synonym for the oblate spheroid representing the shape of the Earth is a geoid. All of these variations are accounted for in a spatial reference system, or coordinate reference system, which is a framework used to precisely measure locations on the surface of the Earth as coordinates. These are sometimes called coordinate systems, but technically speaking, a coordinate system is only a part of a complete SRS, which also includes a specific geoid, a point of origin, a region of validity, unit of measure, and an optional map projection for regional or local systems that aren't expressed directly in latitudes and longitudes. Many thousands of spatial reference systems exist, each optimized for a different purpose and occasionally for a specific range of time, since the Earth's surface is always in flux due to tectonic activity and the like. Any feature class, or sometimes an individual feature in a GIS dataset, typically carries a spatial reference system so that users and software can interpret their true locations on the planet. When you make a map, as opposed to a globe, you are necessarily projecting the curved surface of the planet onto the flat surface of whatever material or screen you're using. This process unavoidably distorts the shape and size of the planetary surface features, each to varying degrees. There are so many defined and possible map projections that it would be impractical to count them. Suffice it to say that different projections are optimized for different purposes and regions, and no projection is perfect. The Mercator projection, represented above, is the most well-known, though it's rarely used by professionals because it enlarges features the closer they are to the poles. Indeed, were one to try to extend a Mercator map to the poles, each pole would have to be represented by a line, even though there are merely points on the Earth's surface in 3 dimensions. When working with spatial data, one often needs to interactively define a region with which to work, such as a pre-existing political boundary or a custom-drawn box or polygon on a digital map. This is known as an area of interest, or AOI for short. Without AOIs, the volume of data coming back can sometimes be impractical, both in terms of human or perhaps even technological capacity, depending on the scope of the query dataset. CAD, or computer-aided design, is another spatial technology closely related to GIS. It represents the use of specialized software to aid in the creation, modification, analysis, and/or optimization of physical designs, usually of buildings or other engineered structures. CAD datasets are typically not georeferenced, which means they are not explicitly oriented within a geographic frame of reference that would place and orient them with respect to the planet. Architects and engineers are CAD's primary user base. Building information modeling, or BIM, is a process supported by various tools, technologies, and contracts involving the generation and management of digital representations of physical and functional characteristics of places. I think of BIM as like CAD on steroids. The level of detail is much greater and is often sufficient to render a high-fidelity virtual version of a building inside and out, including utilities and other behind-the-wall features. This is of the Clinton Presidential Library, by the way. It's in public domain, so. A digital elevation model, or DEM, is a 3D representation of elevation data to represent terrain. In GIS, DEMs can be represented as rasters, where each cell contains an elevation figure. But they can also be represented as interlocking vector-drawn triangles in a 3-dimensional mesh. An unprocessed DEM is often represented as a grayscale image, like this one, where higher altitudes are brighter. They can also be rendered in false colors or be used as a surface over which to virtually drape photographic land images. A lot of 3D models are created by advanced radar-like technology. One such technology that's rapidly gaining popularity is LiDAR, which stands for light detection and ranging. It determines ranges by targeting an object or surface with a laser, measuring the time for the light to return to the receiver at varying points. This process usually results in a special type of 3D vector geometry called a point cloud. Point clouds can then be post-processed in many ways, including surface modeling, object detection, or filtering out unneeded layers like vegetation. Now turning to some categories of spatial data sets. We have the GIS mapping file formats, CAD architectural and engineering design drawings, full-fledged databases with spatial data types, operators, and functions, building information models, other 3D formats such as point clouds, game engine, and mixed reality models, and spatial and spatially enabled web services and other APIs. There are many hundreds of commonly used spatial dataset formats out there. Also, just about all of the major enterprise database vendors support spatial extensions. Spatial data is stored and accessed in many ways, usually dependent on the specific format. Some are stored as an individual spatial data file. Others are stored in a flat or deep hierarchy of files within a directory, often requiring zipping or other archiving to share as a unit. Still others are stored in a spatial enterprise database, as I mentioned in the previous slide. Also, as mentioned in the last slide, some spatial data is accessed as needed from specialized APIs. Finally, some data is generated and sent real-time in small packets. Such data is said to be streamed. For example, active sensors, GPS trackers, Internet of Things devices, and remote system data monitors can all stream data with spatial components. All this data can be collected, processed, stored, forwarded, and analyzed as needed. So you think ignoring spatial data in an organization's integration strategy is a good idea? How many bad decisions could this lead to? How many bad decisions can an organization afford? How many bad decisions would you want to make? I submit to you that spatial data can and should be included in any organization's integration architecture, as it's just as important for effective decision-making as all the rest. Here's a smattering of industry-independent applications for spatial data integration, including format translation, restructuring, multi-data set blending, data validation and cleansing, geospatial analytics, data warehousing and data marts, geospatial business intelligence or BI, self-service, business process automation, enterprise service bus, backend for mapping apps, real-time sensor data collection and processing, data synchronization, sensor data interpretation and modeling, and pretty much anything you can imagine doing with data in general, plus spatial. Many of these should be familiar to non-spatial data integrators, but special algorithms and tools are often required to make them work with the spatial components, especially when spatial-only data formats and processes are involved. Geometry cleansing and validation, geospatial analytics and maps-based presentations, and support for mapping applications are uniquely dependent on proper methods and tooling. In addition to these, there are specialized spatially intensive use cases for many industries that are beyond the scope of this presentation. Of course, as with any data integration, there are problems to be overcome including these common challenges. For one thing, GIS grew up largely independently from the more general IS/IT field, and so includes many unique data formats, algorithms, tools, and practices. This historically made it relatively unknown to the larger IS professional world, except in cases where there was an obvious essential need, such as in land research and management. That is, until Google Maps and its ilk became popular in the mid-2000s. The launch of its public API in 2005 made some mapping-specific elements of GIS available to the masses, which completely remade the landscape, pun intended, and put GIS concepts and tools into the spotlight, along with all the other challenges associated with the use and integration of spatial data, such as incomplete and dirty data, data sets with incompatible spatial reference systems and formats, a dearth of spatially aware user interface support, and even where all of these problems are absent or resolved, geometries from the same or multiple sources that don't mesh together intelligibly. Many of these challenges should be self-evident, but I'll cover a couple in greater detail to give you a flavor for them. Incomplete spatial data creates similar issues with its non-spatial cousin. You wind up with an incomplete vision at best, or more likely, a misleading vision of the truth on the ground, so to speak. Additionally, there are many ways for spatial data to be downright wrong. For example, hand-drawn CAD geometries often result in what are supposed to be closed polygons, but aren't. Consider these residential neighborhood lot lines. They should completely enclose their corresponding home lots, or they should meet without overlapping, but they often do not in the real-world CAD drawings. This becomes important when you want to do things like measure the area inside each lot. There are many other ways that vector geometries can be inconsistent with themselves, such as self-intersecting polygons or otherwise impossible objects like those in an Escher drawing. They can also ignore standards that dictate things like whether a ring of points defining a polygon or a hole in a polygon should be clockwise or counterclockwise. One more kind of dirty spatial data I'll mention is that of noise, so-called, in point clouds, taken by a LiDAR scanner or similar instrument. These are outliers that don't represent the target object or surface, and may be caused by things such as rain, dust particles, or other transient phenomena in the air between the scanner and the target. There are methods and tools to detect and deal with these, including some I've authored. Just don't ignore any of these issues if you want to derive true value from your spatial data sets. Another problem that most often occurs when blending data from different data sets is misaligned geometries that should line up perfectly to reflect the real world. Consider the boundary between these two regions, representing some, hypothetical squarish counties. There shouldn't be any single point that exists in both counties at once. But as you can see, that is not the case here, since the county boundaries slightly overlap in places. Additionally, there are points that should be in one or the other of these counties, but are inside neither county polygon. This situation has many potential causes, including different data sets recorded with different levels of precision, moving landmarks, and surveys from different eras. It also happens more often with regions that have more irregular boundaries, which is a much more common occurrence in the real world. As before, there are tools and methods for dealing with this, but knowing the problem exists is the first step in dealing with it. There are many kinds of tools spatial data integrators can use to accomplish their goals. These include tools for spatial professionals, as well as some emerging tools for non-spatial users that need to work with spatial data. And there are other classes of tools, including geodatabases, other kinds of spatial data servers, custom code libraries and application frameworks, open standards that make it easier to share spatial data, and integration platforms that make it possible to share even more types of spatial data. These are core tools used by spatial pros themselves. The most prevalent of these is the commercial ArcGIS suite by Esri, the Environmental Systems Research Institute. Esri is the 800-pound gorilla in GIS, with tons of interactive mapping and analysis features, plus some scripting libraries to enable automation using programming languages such as Python, Java, and JavaScript. There are some less popular yet powerful open source alternatives to ArcGIS, such as QGIS and GRASS. For CAD practitioners, the most popular tool is the commercial AutoCAD suite by Autodesk, which also includes some building information modeling and related applications. And as with the GIS tools, there are some open source alternatives such as LibreCAD and FreeCAD. And in some 3D game, mixed reality, and animation tools, like the open source Blender and its commercial cousins, and you can have a wide range of tools that include some spatial data import and export capabilities for spatial data integrators. However, these capabilities are typically restricted to tool-specific subsets of the plethora of spatial data formats in existence, and they're not always easy to script or automatically manipulate. Some of these tools tend to favor their own proprietary dataset formats, encouraging vendor lock-in. They all potentially place diverse sources of spatial data out of reach.
Kevin, I have a question, if I may.
Sure.
This is Jed Somerton, and I've seen a lot of references to GRASS as a GRASS data set. Is there anything particularly special about GRASS, or is it just another software package with proprietary data?
Well, I mean, it is a software package. I haven't used GRASS myself directly. It is open source. I don't know if it has its own specialized formats or not, but it is open source, and so it should be fairly accessible.
Okay, fair enough.
Yeah, I don't know off the top of my head whether or not it has any of its own specialized data formats. I haven't encountered them in my professional career so far.
Okay, thanks.
Sure. These are a few examples of tools meant for use by spatial laypersons. Everybody knows how to use Google Maps, and Google Earth is also widely known and used. OpenStreetMap is an example of a non-proprietary option for crowdsourced maps and mapping data. Equator is an example of a new and lesser known tool for the masses to access elevation data. Alteryx is an analytics platform, it's commercial, with good spatial support for non-spatial professionals. As with their professional equivalents, built-in import and export options provided by these tools are typically restricted to a few options. Both enterprise and local geodatabases also offer some very limited import and export options out of the box, though they do often include some scripting capabilities. Obviously, they're databases, and they can and are often used with more robust geo-integration tools to store and retrieve spatial data. Examples of databases with spatial support include Microsoft SQL Server, Oracle Spatial, PostGIS for PostgreSQL, Spatialite for SQLite, and Esri Arc SDE for several relational enterprise databases already mentioned here. You may also notice some NoSQL databases listed here, such as CouchDB and Elasticsearch. There are other special purpose spatial data servers, including ArcGIS Enterprise and ArcGIS Online, GeoServer for open standard APIs and map tiling access, the proprietary enterprise spatial search engine Voyager Search, and Tableau or Click for analytics dashboards. Again, These support some restricted sets of data formats, but they are not really designed for broad integration of any spatial data form in any format, though they are powerful and do have their legitimate uses. You can always write custom software to read and write just about any spatial data format you could ever imagine. There are many code libraries, both open source and proprietary, to help you do this. Both Esri and Autodesk provide APIs for their tools and data formats. Open source libraries include the Geospatial Data Abstraction Library, or GDAL, the Proj library to support spatial reference system reprojection, and more. Some spatial user interface frameworks, such as OpenLayers and Leaflet, can help you generate mapping apps. Esri includes similar facilities within its proprietary suite. Of course, coding can be very time-consuming and resource-intensive, depending on your needs, but it's an always available and sometimes a necessary option. One strategy to make spatial data integration easier is to stick with data formats and APIs based on open standards. Several organizations have created such standards, including the Open Geospatial Consortium, or OGC, and the International Organization for Standardization, or ISO, Technical Committee 211. There are many standard spatial data formats, such as GML, KML, GeoJSON, IMDF, and more. KML is kind of a special, it's really meant for use with Google Earth, but it's been adopted pretty widely. IMDF is Apple's indoor mapping data format. There are also many standard web service definitions, such as Web Feature Service, Web Map Service, and Web Map Tile Service. Focusing on open standards where possible is not a bad idea, but these formats and API schemas are far from universally used or supported by the tools and APIs you may need to use for all your integration requirements. Which leaves us with platforms designed to support universal data integration, typically with extract, transform, load, or ETL features. There are, of course, the usual suspects, such as Informatica, Tibco, MuleSoft, etc. But these are far from capable of handling most spatial data formats and operations, as they were not designed with spatial in mind. We can see Alteryx again here, but as I noted previously, it too is relatively limited in its support for spatial data formats. The only platform with truly comprehensive support for spatial data is FME by Safe Software out of Vancouver, Canada. I use FME for the vast majority of my spatial data integration and ETL needs, largely because it dramatically speeds the process with its graphical data flow configuration paradigm and full enterprise process orchestration capabilities. It literally supports many hundreds of spatial and non-spatial data formats out of the box. So it'll work for just about any data integration, not just spatial. FME tends to get me to a complete solution several times faster than custom coding for most such applications. It's also less expensive than most, if not all, of the other commercial options in the field. I've assembled my own extensive private kit of FME-based tools over the years. These do everything from batch and real-time geo-aware enterprise database synchronization with Salesforce to integration with other common software as a service providers like QuickBooks Online, to special attribute value formatters, to name and address parsers and cleansers, to some specialized address locators, which are known as geocoders in the field. I've also published open source tools on the FME Hub catalog for base64 encoding raster images as PNG files suitable for embedding in HTML, as well as a whole suite of geometry and attribute validation and reporting tools. I'm sure many of you are familiar with the old industry adage, garbage in, garbage out. As I've already mentioned, dirty data can wreak havoc on the reliable operation and results from any data-dependent system, including a spatial integration and processing system. This is the very issue my FME geometry and attribute validation toolkit is designed to address. It combines some of FME's built-in validation tools with a framework for automated data validity testing and reporting. Here's an example of a geometry validation report generated by these tools. The intent is to apply automated testing methods from software engineering into the spatial integration realm, where it's not quite as well known. I use these all the time in my FME projects to ensure correct and reliable ETL results, even as the tested workflows themselves evolve over time. So if you're tasked with integrating data that includes spatial components in the mix, here's what I suggest you do. If you have very narrow spatial data requirements that happen to be met by any of the tools supporting limited integration capabilities, feel free to use those as appropriate, especially when those tools are already in use. If you need to consolidate spatial data in a traditional database, use a spatially enabled database management system, adding geometries to any tables containing spatial data. Use FME as your data integration platform if you want to be able to use a very diverse array of spatial data formats and processes, or at least include FME in the mix to handle any spatial integrations directly. Don't neglect your spatial data. Keep it front and center as a key organizational asset. Write any custom code you need for the most esoteric spatial integration requirements. But this should be kept to the absolute minimum, as both implementation and maintenance of custom software is resource intensive. And finally, use any specialized data servers as necessary to support your mission to bring spatial data to your organization's user base so they can make the best decisions possible. Now I'll cover just a handful of examples of spatial integration projects from my own professional history. The first is a self-service system for White Star Corporation's spatial data mart. The clip zip ship service, you gotta be careful when you say that one, you can't say it too many times. The clip zip ship service within the White Star Cloud platform uses FME server to parse data requests from its customers via web application or specially formatted email, extract them from its PostGIS database, export them to any of a large number of possible spatial data formats, temporarily store the results, and notify customers when they're ready for download in the requested format. Users can specify an area of interest, identify the datasets and layers within, specify the spatial reference system for the output, choose the output format, and finally submit the order. This solution does call into a custom Python library I wrote to authorize the user, parse the request, and translate it into the appropriate spatial database query. Not all projects require this kind of custom query generating program logic, but the range of customer requests possible is very broad in this case. And the underlying data schemas were extremely varied and somewhat inconsistent with each other due to historical reasons. Though White Star did at least some work to standardize their database schemas so as not to make the software requirements more onerous than they absolutely had to be. Another client had a very similar data mart requirement, but with far fewer schema variations and much simpler requirements overall. So only a couple of FME workflows were necessary with no custom code involved in the solution. Here's an example of one of the FME workspaces. A workspace is a single workflow file in FME world. Multiple workspaces can be composed into complete solutions quite easily. Here's a brief excerpt from a custom Python integration solution for a large commercial real estate company. Sometimes custom software is necessary for political as well as technical reasons. This was one such case. I estimate that it took me at least 3 to 5 times longer to implement this solution than it would have with FME. But it works, so there's that. Given my background in software development, I am perfectly willing and able to write code till the cows come home. This same company also needed a corporate spatial search engine. So I installed and configured a Voyager search server for them. Another client, Bluefin, needed GIS files from surveyors automatically converted into CAD files in a prescribed catalog layout for roof maintenance engineers and inspectors to use. This required a fairly elaborate solution involving multiple FME cloud workspaces, plus Amazon Web Services storage and queue services to automatically pick up and convert incoming GIS files into AutoCAD drawings and corresponding image files. The resulting drawings required optimal automatic scaling and placement of building layouts on the page, all possible with FME. No custom Python was required for this solution. And that's all I have for today. Hopefully I've given you a flavor for spatial data integration that you can use in your own solutions moving forward. And hopefully I've managed to convey the importance of spatial insight for optimal decision-making in the modern world. Please feel free to get in touch if you are so inclined, and thank you so much for your time and attention today. I'll stick around for any further questions or general discussion. And so maybe a little shorter than typical, but I was always taught that you should never go over 35 or 40 minutes in a presentation. So
Kevin, I got a lot out of that and I greatly appreciate it. Question for you. If we wanted to get started, I haven't used GIS before and I don't want to pay for ArcGIS and Esri and all that kind of stuff.
right.
What open source or freeware would you recommend and what's the best way to get started with it?
Well, let me see let me go back to that slide even. That might even be helpful. Well, wait a minute. Well, I mean, I don't know how in-depth you want to get or what exactly your applications are. It may depend. You know, like I said, the alternatives to Esri are QGIS or GRASS. I personally have not used those in great detail. I usually interact with people who do, but those are the biggies in GIS for kind of professional analytics. So that's where and as far as how you learn them, I'm sure there are a lot of resources. I'm trying to think if there might be. So I didn't mention that I'm also an instructor at Bootcamp GIS, and my course is about using FME for the architecture, engineering, construction industry. But there may be at bootcampgis.org, there may be another course that teaches you how to use QGIS or GRASS for some applications. That's an option. Some online boot camp of some sort may be an option. Most of these tools have their own websites as well, and they'll probably give you pointers on how to learn these things. And as far as, I mean, obviously there are, again, if you're trying to do spatial analytics, Alteryx, I understand, is pretty easy to use for lay people. It's not designed, that's what it's designed for. But I mean, I'm not sure you're not a lay person, but I don't know if you're, spatially it may be a somewhat different world. So I mean, although that's that's of course commercial. So I don't, and then I think Alteryx is pretty expensive, but if you're talking about specifically GIS, standard GIS tools, I would say QGIS or GRASS would be the place to start. Will that work? I wonder why my volume coming in is so low. Let me see if I can, I don't know if anybody else is going to ask questions, but it's really like super quiet. Let me see if I can change my audio. In fact, let's do this. So I'm going to stop my screen share as a matter of fact. Am I supposed to stop recording at this point? Do you, any of you know if I'm supposed to stop at the Q&A?
Stop at the end.
Hang on, let me. It is so quiet. Let me see what he said here. Let's see. All I know is that once I stop the recording, Zoom takes about an hour to compile, and then Bob is going to collect and post process. So let me see. There we go. Any other questions?
Yeah, I got a question, just curiosity. Do you know if there's any predominant forms or differences in use of GIS in supply chain?
You're talking about how they use it in the supply chain? Yeah,
No. Well, how they, well, I was thinking more in the formats and or if there's any specific software. Just I may end up getting involved in supply chain at a large company. So
that's an interesting question. I imagine there is some specialized software out there. I have not used it myself. As far as formats go, that is a good question. I imagine in supply chain work, they're doing a lot of routing and things of that nature. And a lot of these tools will do that. I'm wondering if I were to say, if I search like FME again, since that's kind of my majority go-to tool, if they like I said, they literally have hundreds of formats, and I'm wondering if I did a search on supply chain, would it actually find something? But no, nothing that's really specific to that. I mean, I think a lot of generic formats would still work for those.
Yeah, I was just curious, since I know I've dealt with some of ArcGIS and Esri and stuff, but I haven't dealt with supply chains before, other than gross level. So just curious.
Right. That's that, and I truthfully I haven't either dealt with that. I keep on thinking it's a great market. I do know there are specific formats for certain other industries, like utilities will use, there are specialized formats in the ArcGIS world for utility management and data management. And I think there's Small World is General Electric. Format for managing like electrical utilities data and so forth. And so there are a lot of industry specific formats out there, and I know FME handles a lot of those. Yeah, against supply chain, I have no experience with it, so who knows what they do. Good question though.
Thanks.
Thank you.
Yeah, thank you.
Let's see. Oh, John, let's see, says I'm currently working on spatial temporal database benchmark. We're also including Kinetica and Heavy.ai. Azure Cosmos didn't work as well. That's interesting. That is interesting. There is definitely a movement in GIS toward, adding time as a dimension. And I mean, even some of the newer spatial reference systems. One parameter for conversions using newer spatial reference systems coming out is time, because things do move. Not only does plate tectonics move, obviously, I don't know how many of you realize that the magnetic poles move, and they're moving more in recent times than they have in the past. So I wonder when eventually the North Pole become the West Pole. Anyway, just a little thing. Yeah, John, I definitely am interested. I'll follow up with you on that. And Richard says, yeah, GRASS, the GitHub, quite active. Yeah, I guess they're continually improving that piece of software as well. My work is usually involved in integrating the data that people who use those tools use. So it's its own kind of a skill set that GIS analysts work with. So all right. Anything else? Well, I'm gonna go ahead and stop the recording then, as soon as I figure out how. Just a moment up here.